and this is the last chapter in this course. Okay, now we are like in this chapter mainly we are talking about the laws of thermodynamics. Then we did talk about the zeroth. We are going to talk about the first law of thermodynamics, and we are going to talk about the second law of thermodynamics. Okay, we're going to review what we said about the zeroth law of thermodynamics. We are going to introduce the first law of thermodynamics and the special cases like the thermal processes that we might include for the first law. We are going to now specify more the specific heats for ideal gas at constant pressure and at constant volume. We will introduce the law of thermodynamics and its relationship with heat engines and the Carnot cycles. We will talk about refrigerators, air conditioners, and heat pumps. We will talk about entropy and how it is related to order disorder, and we will talk about the third law of thermodynamics. Now, we did discuss this before about the zeroth law of thermodynamics. If we have an object A is in thermal equilibrium with B and B is in thermal equilibrium with C, then A should be in thermal equilibrium with C. Okay, and I told you this one doesn't need a proof. It's a common sense thing, and this is the reason maybe why it is zeroth. Now, thermodynamics, it is the study of the processes in which energy is transferred as heat and work, and we are going to study also changes in internal energy. We will talk about different types of objects or systems. A closed one where is no mass enters or leaves but energy can be exchanged, or open where mass and energy may enter or leave, or isolated, no mass or energy crosses the boundaries. And we will talk about this in a little bit. Now, we have here, the general form of, let's say, conservation of energy, and that is really related to, say, okay, energy before equals energy after. We can also we can also say that this is true for thermodynamic systems. Then the change in energy in a closed system is equal to the heat added to the system minus the net work done by the system. This is we call this the first law of thermodynamics, and it has to do with actually conservation of energy. Then it's telling you that the total energy of the system is dependent on two things. One of them is the heat added or removed from the system and the work done by or on the system. And these words are very important, like on and by, and I will clarify this in a little bit. Now, the change in internal energy, and here I want to also clarify about the change. Always it is final minus initial, because this can be negative or positive. Negative means that there has been a decrease. Positive, there has been an increase. The change in internal energy of a closed system will be equal to the energy added to the system minus to the work done by the system of its surrounding. Now, why we said like the energy added? Because here Q is here, Q it is positive. And the work is going to be positive when it is by the system in this equation. By the way, we have so many forms, not so many, like I think maybe there is an alternative form of the law that is using a different convention. This one we will not use it, and in the exam I will expect you to use ours. Okay, and here for the Q, it is positive when it is added. Now, Okay, and this is vital to keep track of the signs. Q positive when the system gains heat, Q negative when the system loses heat, W positive when it is the work done by the system, and W is negative when the work done on the system. Okay, then now here we are going to say what if it is not a closed system? The equation works also for open systems if you take into account the changes in matter, and also it is working for isolated system. Okay, and we will clarify this more in a little bit. But just what, like, the soul of the law is telling you that the internal energy of the system depends on temperature. We will see that, and we will know that the work done and the heat added, they depend on the details of the process involved, which means so many times you are going to find like delta U, like the change in the internal energy is going to be the same, but we can do that through different processes. Okay, and we will see maybe some of these examples. Now, the internal energy of the system, remember we did this in chapter 17. I will use that equation here. This is for U, 3 over 2 NKT or 3 over 2 nRT. And we are going to actually use that for the calculation of U. We will assume in all the processes that they are quasi-static, which means they are slow enough that always the system is going to be considered in equilibrium. Also, these processes are considered to be reversible. For a process to be reversible, it must be possible to return both the system and its surrounding to exactly the same state before the process was beginning. For example, here, this is one of the idealized reversal process. The gas in the first one here, it is really compressed, and the temperature is constant, so heat leaves the gas. As the gas expands, it draws heat from the reservoir, and returning the gas and the reservoir to their initial states, the piston is assumed to be frictionless. Okay? Now, I will use some of the terms here. Isothermal means that the process, it is occurring at constant temperature, which means PV equals a constant. Adiabatic means Q equals 0, no heat flow. And in this case, we are going to have delta U equals negative W. This is the special case of the first law of thermodynamics. When it is isobaric, that means the change in P equals 0. Okay, which means here that we can use a special formula for the work done, which is like we can say W equals P times delta V. Now for isochoric means constant volume, and when it is constant volume, the change in V is going to be 0, and the work done is going to be 0 as well. And here we are going to have the special case of delta U equals Q. Okay, now let's go over process by process. The first one here, it's an isothermal process, one where the temperature does not change. Then we said like here, delta T is going to be 0. Now, when delta T is 0, then delta U is 0 as well. And I will say here, of course, we can use the relation PV equals constant, because now we can apply Boyle's law. All right, and this is the isothermal. When and we said that before, these are isotherms. If the temperature is constant, delta U, which is 3/2 nr delta T, is going to be 0, and because of that, Q will equal W. When we have an adiabatic process where there is no heat flow into or into the system or out of the system, then Q is 0, and here delta U equals negative W. And we can find that delta U equals negative W equals 3/2 nr delta T. U goes down if the gas expands, and T decreases as well. If W is done on the system, U and T will go up. And just here, I want you to know that the isothermal and the adiabatic, they are looking the same on the PV diagrams, because we are using these PV diagrams widely. And just I want you to know that the one that is steeper is going to be the adiabatic. Because you might have things that where we are going to, maybe include like diagrams, not only information from the question. Now, we said here the adiabatic process, it is in one, no heat flows into or out of the system. And we might have an insulation. PV curve is similar to the isothermal, but it is steeper. One way to ensure that the process is adiabatic is to isolate the system. Another way to ensure that the process is effectively adiabatic is to have the volume change occur very quickly. In this case, heat has no time to flow in or out of the system. Now, when I have isobaric, the process is gonna be that delta P is gonna be 0. Okay, and when it is delta P equals 0, I can use the work done as W equals P times delta V, and this is when I have only constant pressure. And you can see that the PV diagram is going to be just a horizontal line like this. And remember, always the area here under the curve is going to be the work done. Now, when we have isochoric or isovolumetric, delta V equals 0. And that is where the process we're gonna have the work done is 0, and then delta U will equal Q. Now, on the PV diagram, this is looking as a vertical line, and if the volume stays constant, nothing moves and no work is done, and W is 0. Now, the work done is the area under the curve of your PV diagram, then is going to be Q equals W. In this case here is going to be area under the curve, and here W is 0. Now here, summary of different types of processes where for constant pressure you have W equals P times delta V. For the constant volume, W is 0, and W is equal to the Q. When I have isothermal and adiabatic, W equals minus delta U. And here, this is how really the first law will change. Now let's try this. An ideal gas expands isothermally, performing 3.4 10 to 3 of work in the process. Then the gas is doing the, then the work is done by the gas. Calculate the change in internal energy of the gas and the heat absorbed during this expansion. Now, delta, of course, isothermal means delta T is 0, then delta U is 0. And what I was talking about also is that delta U will be Q minus W. And I can say that Q will equals to the work done here. That's it, as easy as this. The second one, it is considering the following two-step process. Heat is allowed to flow out of an ideal gas at constant volume, so its pressure drops to 2.2 atmosphere from 2.2 atmospheres to 1.4 atmosphere. Then the gas expands at constant pressure from the volume of 6.8 to 9.3, where the temperature reaches its original value. Calculate the total work done by the gas in the process and the change in internal energy of the gas in the process and the total heat flow into or out of the system. We can treat this as a complete process, and you can see here that the first one, which was, heat is allowed to flow from at constant volume. So the pressure, then this is the first process, and then this is the second process. Okay, now, we can say delta U equals Q minus W, and Q will equal delta U, which is 0, plus the work done, which is 3.5 10 to 2 joules. And that is part C. The total heat flow into or out of the system. Q is positive and the gas gains heat and the flow is into the gas. Now for the second, for A, the total work done by the gas. Now during 1, 0. Why? Isochoric. For the second part, it is P times delta V, and I'm sorry. And is going to be the pressure was constant as 1.4 atmospheres times, I need to convert this into pascals, times the change in the volume. It is 9.3 liters minus 6.8 liters times 10 to minus 3. And you can see here I have the the conversions here. Then I will say, I will say that 9.3 minus, okay, yes, okay, 9.3 minus 6.8. This is going to be the 2.5. Okay, then here, what I will do, 1.4 times 1.01 times 2.5. Okay, this is 3.535, and this is 10 to 2 joules. And this is the value, of course, like, just making kind of the sig fig to have W here. Now the change, B, the change in the internal energy of the system. Okay, in the whole process, like it expands at constant pressure from the volume where the temperature reaches its original value. Because we did reach the same value, then delta U is going to be 0 because delta T was 0 because it did reach the same temperature. And then I have here part 3 where Q is going to be 0 plus 3.5 10 to 2 and is going to be positive. And this is the reason why is going to get positive. Now, one more thing I need maybe to indicate here, which is, the work here, the total work done by the gas in the process. I have calculated that, and I have included in the calculation. A 1 liter volume of air initially at 4.5 atmospheres pressure is allowed to expand isothermally until the pressure is 1 atmosphere. It is then compressed at constant pressure to its initial volume, and lastly is brought back to its original pressure by heating at constant volume. Draw the process on a PV diagram, including numbers and labels for the axis. We need to find one more label, which is at the isothermal. We have delta T, which means PV is constant. Then I need to calculate what are really the pressures and volumes. Okay, and I will say initially it is at 4.5 and then it will expand isothermally. Then this is number 1 and is going to go to 2 isothermal, and it will reach the pressure which is 1 atmosphere, and then it is compressed from 4.5. This is V2 to V1, which is 1 liter, and then it will brought back to its original pressure, which is the 4.5 at constant volume. Then this is number 3. Then it's gonna go, the first one is going to be from 1 to 2, and then from 2 to 3, and then from 3 to 1 again. I will stop here and I will do the second part later.